Hello everyone. In this video, I'm going to talk about the Flash dataset. This is a dataset that we are releasing as part of our recent InfoComm 2022 paper. So let's just start with some background and highlight the research areas that this dataset can be used for. 5G wavewaves is one of the key features of 5G, and it includes applications such as advanced driver assistance, fully automated driving, traffic efficiency, and infotainment. In all of these applications, you either need low latency or high data rate connectivity, and this motivates us for using mmWave band. The mmWave band includes high frequencies such as 60 GHz, and you can achieve gigabit per second data rates in this band. Because of the high penetration loss at high frequencies, we are using directional transmission on this band. And this means that the energy is concentrated in a narrow aperture, or as we call it, beam. In order to achieve the promised gigabit per second data rate in the mmWave band, you need to be sure that your transmitter and receiver are aligned with each other. The way that the current standard do this is the transmitter and receiver are going to sweep all possible beam combinations to identify the best one. And you can imagine that this process is very time consuming. And it's even more pronounced in vehicular scenarios because the vehicles are moving very fast and the optimum beam can change very rapidly. To address this challenge, we are proposing to use the multimodal data from monitoring devices such as GPS, camera, and LiDAR, and use these information as input to a machine learning algorithm to predict the optimum beam and just go for it. So you can imagine that this multimodal data can be used for to speed up the flight tasks such as beamforming, handover, etc. But as always, the challenge in the machine learning algorithm is the scarcity of public data set. So for that reason, we are publishing the real world Flash data set here to the community. As I mentioned before, in the Flash framework, we are using the sensor data to configure the file layer parameters. So in our data set, in one hand, we have the RF ground truths from a Talon AD7200 multiband Wi-Fi router. This router works at 2.4, 5, and 60 GHz. And of course, we are using 60 GHz band here. It has a total of 64 beam configurations. And we are using the Nextmon firmware to access the file layer measurements, including RSSI and SNR. On the other side, we have the sensor measurements. We are using the Lincoln vehicle here, and it has an onboard GPS. The sampling rate of this GPS is 1 Hz, and it returns the latitude and longitude in decimal degree. We also have a GoPro Hero 4 camera that is mounted on the top of the vehicle. The resolution of this camera is 720 by 1280 with frame rate of 60 frames per second. And finally, we have the below-down LiDAR to capture the 3D features of the environment. It has 16 channels with range of 100 meters and field of view of 30 degrees. The precision is up to 3 centimeters, and the sampling frequency is 10 Hertz. So let's first check out our Flash testbed setup. We are running the experiment in an alley with 2 lanes. We have our Lincoln vehicle here. It has one of the routers mounted on top of it. It also has the GPS, LiDAR, and camera sensors. On the other side, we have the other router on top of a sidewalk cart, and we are using the iPerf3 software here to set these two routers as client and server and start the transmission of a stream of data. Using the next mode framework that I mentioned in the previous slide, we can get the RSS of each beam pair in the form of text file. And on the other hand, we have these sensors at the vehicle. All of these sensors are connected to a centralized computer, either by Ethernet, Wi-Fi, or USB. And this computer is running ROS, or Robotic Operating System. Basically, the ROS code enables you to record these sensor data along with their timestamps. If you are not familiar with the ROS framework, you don't need to be worried. We already took care of the ROS part, and you can easily access the data without dealing with the ROS software. So you can imagine that in one side, we have these current rules recorded at the transmitter. We have the RF, we have the sensor data at the vehicle. We collect all of this information and then we run a synchronization algorithm offline and get our processed samples. In the Flash dataset, we try to capture different combinations in the dataset. In particular, we have 4 different categories, including line of sight passing, 9 line of sight with pedestrian, 9 line of sight with static car, and 9 line of sight with moving car. In each category, we have another set of scenarios with variation in speed, direction, and line. For example, in category 4, we have the car moving with a speed of 15 and 20 miles per hour from left to right in the opposite lane. And the other car is moving with a speed of 15 and 20. You can see 2 videos from our testbed setup here. We are repeating every scenario 10 times, or as we call it, we have 10 episodes per scenario. By having this feature, we can imagine that we have 10 different vehicles in our data set, and this can capture like more advanced learning methods such as pedestrian learning as well. Overall, we have 21 different scenarios and 31K samples. In the following slide, I'm going to walk you through the structure of the dataset. Basically, we are releasing two variations of our dataset, the raw data and the process data. I'm going to start the raw data here. So as I mentioned, we have 4 categories, category 1, 2, 3, and 4. And in each category, we have the scenarios. For example, in category 4, we have these 4 scenarios. If you open the directory of each scenario, you can find a zip file named as sensor data. And this zip file includes the sensor data recorded for each episode from 0 to 9. If you remember, I said that we have 10 episodes. And if you open each episode, you again find a CSV file that contains the GPS data, a directory that includes the later PCD files, and each of these PCD files are named according to their timestamp. And we also have a subdirectory for camera images. And again, these images are also named as their timestamp. The other directory that you can find in each scenario is the extract directory. If you open this directory, you will find 10 subdirectories for 10 episodes. And in each of these subdirectories, you find 5 CSV files. I'm going to go over each CSV file one by one in the next slide. These CSV files are designed to collect the important information about each modality and also the RF ground truth data. For the GPS data, we have the first 5 columns to be the experiment information. For example, this CSV file refers to category 4, then the speed is 10 miles per hour, direction is from left to right, and it's in the opposite lane, episode 1. This column shows the timestamp of GPS recording, and these 2 columns shows the latitude and longitude in decimal degree. We are also including a variation of decimal degree measurements, where we are converting these latitude and longitude to an XY point in a Cartesian system. You can choose the one that is suitable for your experiment. The CSV file of image and LiDAR is pretty straightforward. We have, again, the experiment information in the first 5 columns, and we have the timestamp and the path that you can find the associated recording. For the RF, again, we have the experiment information, we have the timestamp, and we have the sector IDs here. And also the RSSI of associated sector IDs. So it's like a one-to-one mapping here. We are also reporting the base sector and associated RSSI. So you can imagine that we have these 4 CSV files about our 3 modalities and also the RF ground truth data. And we are put everything together and generate a synchronized data CSV file, which is basically the mapping of these measurements together. So in the synchronized data CSV file, you have the experiment information, you have the timestamp of synchronized data, and the path to the associated LiDAR data, image file, coordinate recordings, and also the RF measurements. You can directly move forward and use the synchronized data for your experiments. If you are interested in using the raw data, you are more than welcome. But if you want to directly move to your experiments and use it and put your hands on the data, you can use our process data. So the structure of the process is that process data is the same as raw data. We have the categories, we have the scenarios, and we have the extract subdirectory as before. But if you open the subdirectory of each episode, you find an extra MPC directory here. And here you can find 4 MPC files, 3 for GPS, LiDAR, and image, and 1 for the RF ground truth. For the image data, we are resizing the images by a scale of 1/4, just to make it easier for you to load the data. So the images are in the shape of 160 by 90 by 3. For the LiDAR data, we have 1 extra pre-processing step here. As you may know, the LiDAR data are varying in size. So the size of the input is changing for each recording. And that's not very desirable for a deep learning algorithm. So we are using an extra pre-processing step here to map all of these LiDAR data to a 20 by 20 by 20 NP array. For the RF and GPS data, the shape is 64 and 2 as expected. These MPC files are these MPC files can be easily used by using the Python NumPy array. So you can design different experiments for including different episodes, different scenarios, or different categories. If you need more information, please feel free to check our paper here. And if you still need more help, please contact us by using these email addresses here. Thank you for watching this video, and I hope that you find it useful.